Good evening, everyone. I do want to apologize at the start. I am doing this broadcast at home, and there might be some little 9 and 12-year-old that tend to need to interrupt me, but hopefully that won't happen here. So the next section that we're going to be doing is on the ideal gas law, and you may have heard your general chem teachers talk about PivNert. And so good old PivNert. When you don't know what to do with a gas, throw it into PivNert, and hopefully you'll get something that will stick. So what's going to happen here is we're combining Boyle's law, which is pressure and volume, Charles' law, which is volume and temperature, and Avogadro's law, which had to do with the number of moles that a gas has. So if we take a look at PivNert, we need to have things in specific units. Now, unlike Boyle's law, if you had both pressures the same, it didn't really matter what it was. But here, for the ideal gas law, we need to have our pressure in atmospheres. For volume, it needs to be in liters. And obviously we have moles with universal gas constant, and our temperature has to be in Kelvin. So remember that you have to take degrees Celsius and you're going to add 273 to get it into Kelvin. So what is that gas law constant? Well, actually, you guys, the gas law constant is just a fudge factor. We are talking this about the ideal gas law. Well, do all gases act ideally? Of course not. So that's just another thing that makes it difficult to study gases. And so what they've figured out is this little fudge factor that we can put in here so that we can study gases and able to make more predictions. And so our fudge factor is in the units of a liter, atmosphere, Kelvin, and mole. So that's why we have to make sure that we have PivNert in all these situations. And so this is at a given time that the ideal gas law hopefully can be true. It's based on experimental measurements, and those experimental measurements are going to be true in the situation if I have a gas, true if I have a gas at low pressures, okay, close to 1 atmosphere, and high temperatures. And so if this is true, we can say that gases are going to behave ideally. Now, the reason we don't study real gases, like the gases that you're breathing in right now is considered a real gas, is because there's intermolecular attractions. So there's some attractions there between those gas molecules. It makes it very, very difficult to study. And every time you have a different pressure, a different temperature, all of those gases are going to behave differently. So we do our best to use the ideal gas law so that we can make predictions of how our gases are going to act. Now, in deriving the ideal gas law, it's not something that we really need to go into here at this point in AP Chem. So it is something that you can read in your text. It walks you right through it and shows you the derivation of it by taking the combined gas laws. We are just going to walk along and say, yep, we're going to use PivNert, that PV equals nRT, gases behave ideally. Now, I am going to go through these in class, but I know some of you like to work ahead and see if you can do them on your own before I do them for you, and that might be a good idea. So if you have time, go ahead and see if you can solve this problem and get 29.0 liters. And the next problem for the ideal gas law, let's see, what's the volume of oxygen will be obtained? So I have a volume of 1.51 liters of oxygen. So you're going to need to write a little balanced equation here, do a little bit of stoichiometry to arrive at this volume. So I will be going through this in class. If you want to tackle it on your own, please be my guest. The next question has to do with PivNert again, and this one is asking for how many liters of hydrogen gas, and the answer here for this one is 38, a 3 and an 8, 38.4 liters of hydrogen gas, and this is using PivNert again. And so here we're going to talk about our gas stoichiometry. So from the ideal gas law, we can conclude Avogadro's hypothesis here that 1 mole of any gas, the volume is 22.4 liters. Now I know that's not something that knocks your socks off, but you need to really remember that we are talking a mole of any gas. We don't care if a gas is heavier than air, lighter than air, like helium. They all, if I have 1 mole of it, 22.4 liters is going to take up with 6.02 times 10 to the 23rd particles. They are all going to take up the exact amount of space. It's really actually very, very cool. Okay, so now we can talk about different gases, and the molar volumes for these. Now, if we talk about these gases, you can see that we talked about that 1 mole of any gas is 22.4 liters. Now, if we scan down here, you can see in actuality that they are fluctuating a little bit. So why are they all not 22.4 liters? And some of these are acting as real gases. And what is happening here, if I take ammonia down here, which you can see it looks like it's the one that's not behaving ideally, and if we draw ammonia, which we've done a few times in class, we recognize that we have ammonia with, or nitrogen, excuse me, with 3 hydrogen attached around the outside, and we have this lone pair of electrons. So what this does is it makes this side, let me grab a different pen color here, that makes this side slightly positive, slightly positive, slightly positive, and you guessed it, over here is going to be slightly negative. Well, what's going to happen if I get another molecule of ammonia here, and what's going to attract to this? Well, you are going to see that this hydrogen here, or this nitrogen, is going to attract to another hydrogen. And so then we have our nitrogen up here like this. Well, this attraction is going to cause some compression. That compression is going to lower the volume that I have down here. So this is why we do not study real gases. It's very difficult to do that. So you can see that the ones that there is less interaction between the molecules are the ones that are actually very close to 22.4 liters. Okay, let's see. I think I'm going to keep going here, and we're going to keep on going right until we get to the information about our lab. So you can calculate the molar mass of a gas from its density. And your book, again, does a really good job of walking through this. Actually, we are going to do this in lab, and we are going to be able to prove that the pressure is equal to the density of a gas times our gas law constant times the temperature, and it's going to be divided by the molar mass of that gas. So we are going to be doing this with a non-volatile liquid, and we're going to take a look at how this interaction takes place. Now, it has to do a little bit with some of the pressure, and we cannot forget about the kinetic molecular theory of gases, which is what we're going to talk about here next. So if we take a look, it says the partial pressure of each gas in a mixture of gases in a container depends on the number of moles of that gas. Now, notice I did not say anything about the identity. So not the identity. You need to keep that straight here for gases. We don't really care what kind of gas we are talking about. We only care about the number of moles of that gas that we have. And so you can see that the partial pressure of this and how much, you can see these are represented by a small amount of weight here, how much they're able to hold up based upon the number of moles that we have here. Now, I guess in the real world, we would probably have some interaction here with these different type of gases, but we are not going to take that into consideration at this point. So this brings us to Dalton's law of partial pressure. You've heard of John Dalton before. He was the one that first talked about atoms as a solid sphere, and then he continued to do his studies on partial pressure. So for a mixture of gases in a container, the total pressure, PT, is the sum of the pressures that each gas would exert if alone. So this should make sense to you that if you think about right now, you are feeling a certain amount of pressure on your body is exerting that same pressure out. But it is a mixture of the hydrogen gas, the nitrogen gas, the water vapor, all the different pressures of these gases individually that we are feeling on us. And so total them up, and that is the total pressure that our body is feeling. Now again, if we rearrange this for Pivnert, we can say that our total pressure is equal to the total number of moles times the gas law constant times temperature, which is going to be divided by the volume. So all I did is I rearranged for Pivnert, substituted in these totals, and Dalton's law would hold true for this also. So we need to talk about a little bit about the kinetic molecular theory of gases with these pressures. You have to remember that these gas particles are in constant motion. So right now, whatever gas you're thinking of, let's say we have nitrogen. That nitrogen gas molecule that's whizzing by your ear right now is in constant motion, very, very high speeds. The collisions are independent and they are elastic, meaning that they can you can have these different gas molecules that are going to collide together, and they are going to become elastic. The energy is going to be conserved. What you need to think about here is a rubber band. You can pull it in and pull it out and pull it in and pull it out. As long as you don't move past this elasticity point, it's always going to go back to its original shape. That's what we mean, is that the collisions are elastic. So the collisions are independent of each other, they are elastic, and they are in constant motion. This is why we can say that Dalton's law of partial pressure is going to continue to be true for any gas, real or ideal. Okay, so moving along here, let's see, was that the next slide? Okay, so we have some more problems that we're taking a look at here, and we will do these again in class, but if this is something that you would like to do ahead of time, it's asking for the partial pressure of each gas in the above mixture. So you should get an answer of 52.2 atmospheres. So go ahead and see if you can get that one figured out. And I think I have a couple more board problems here for you. Molar mass here is going to be 44.1 grams per mole. You should recognize that unit for molar mass. And this next one has a lot of different ways that you can work this one out. So it says how many grams of the dry carbon dioxide gas were produced. You guys are going to see a lot of this working through when we do our lab. So 0.488 grams of carbon dioxide. That one's going to be a little bit more challenging, so see if you can do that one. And then the last one is going to be 1.11 grams of calcium carbonate. So see if you can also work that one out. Okay, so the fundamental characteristics of the ideal gas. So this will be our last slide here that we're going to talk about here. And you need to keep in mind that the volume of the individual gas particle is not important. We are not talking about the identity. We are not worried about that for ideal gases. The force among the particles is not important. We are assuming that the intermolecular attractions are going to cancel each other out. That is why we're using our gas law constant. If these were going to be important, then we'd have to worry about the interactions, the pressures, the types of collisions, the temperature. We'd have all these other factors that we have to really take into consideration, and we don't do that. So again, you need to remember that the pressure exerted by an ideal gas is not affected by the identity, only by the volume of the individual gas particle. The volume of the individual gas particle is not important either, and the force among the particles is not important. Okay, why are we saying it backwards like this? I'm very sorry. So we are basically just taking a look at PV equals nRT. We are taking a look at how those pressure molecules work together in an ideal world. And again, we talked about that they have to be at very low pressures and high temperatures. I'm sorry I messed up this last slide. We will talk again about it in class. I think I need to be done talking now. So you guys have a wonderful night.